Okay, introduction to digital signal processing again. We started in chapter 3, and I have done that part, up to that part on the previous CD, which is the 3A, CD 3A. So the CD 3B, I'm going to start with introduction to digital filter. Before that, I would like to do two examples based on what we have done. One of the examples is that if we have got a digital communication link, which has got an input signal of 3 cos 600 pi t and 2 cos 1800, the link is operating at 10,000 bits per second, and each input is quantized to 1024 level. That means roughly 10 bits. What is the sampling frequency, you've been asked? So what you do is work out the bits per second, which is given already, and number of bits you need is 10,000, 2 to the power b is equal to 1, 2, 4. So that means b is equal to 10. So 10,000 divided by 10 give you 1,000 samples per second. So which is 1 kilohertz is your sampling frequency in this case. And the second part is what are the frequencies in resulting discrete time signal? What are the frequencies available? So we know from here divided by 2, because omega of 2 pi f t is your frequency. You've got pi f, so divided by 2 will give you 300 hertz, and 1800 divided by 2 is 900 hertz. Naturally, you can see your sampling is 1 kilohertz, so half the sampling is going to be fs over 2, that's the folding frequency, is 500 hertz. This is less than 500 hertz, so there will be no aliasing. This is greater than 500 hertz, so it's going to be affected by aliasing. So the aliased frequency that we have to calculate is the new aliased frequency. Is the frequency which you have, which is 900, the k is 1, minus the sampling frequency will give you minus 100 hertz. So the answer to this question is, what are the resulting frequency? 300 will be there without unaffected, whereas the 900 will be translated to minus 100, there's a minus 100 hertz. So that's how you calculate the aliasing frequency. We did some examples yesterday, but I just want to reiterate these examples. I want to do one more example based on the lecture. This is also based on aliasing. Have a look at the spectrum. They've been given the spectrum, analog spectrum is given, and the spectrum occupies a bandwidth of 8 to 10, minus 8 to 10. Okay? So you can see here, this is your equation. When you convert an analog spectrum to digital spectrum, you can have it plus or minus, both works out. And this is the equation. That means analog spectrum is in the digital domain is repeating. That's what exactly it is. So let's look at the sampling frequency. You can see the sampling frequency is here. So sampling frequency here means you will expect half the sampling energy here. That's what you will expect. But you have no energy there. You can see that in the original spectrum there's no energy there. But I told you yesterday that in the previous slide, if you have a sampling frequency which is lower than the energy available, then you can actually work out, if these are multiple, you will see some of these will be translated into the fundamental region. It will be translated here. So we need to find out the aliased frequency. So let's start by sampling at 4 kilohertz, this spectrum, would there be a problem? Let's have a look. Let's say, what's the aliased frequency? This is the aliased frequency. It's the frequency minus KFM. Okay. So we are looking at 8 kilohertz. So 8 minus, we've got sampling at 4 kilohertz, and multiply by 2. I don't have here 1, I'm using 2. You might ask why. Because if this is the half the sampling frequency, if this is normally 1, this part, this will become 2. But you can try out anything you want, 1 or 2 or 3. If I put 2, you can find out the 8 kilohertz is going to translate into 0 hertz. And when I try the next edge, which is 10 kilohertz, 10 and the k equal to 2 times 4, that's this is a multiplication sign. Yeah? That's a multiplication sign. And this also, and you get 2 kilohertz. So naturally what you're saying is this region, that is thou one, that region, that much, is going to be aliased between 0 and 2. So you are going to see a signal there, basically here to here. That is translated from this one is moved in there by aliasing. Now you keep calculating the next frequency, 8 and 0, and if you put 3 and like 3 here, and calculate that again, when you do that, you go, it sees that -4 and -2. So the same signal is also reflected in the region -4 and -2. So you will see a signal here as well. So you can see this signal, original signal, is aliased into the fundamental region here and also just outside the fundamental region. Fundamental region is half the sampling, because this is pi, this is -pi. Don't forget that. Now you go on and recalculate and see what happened to this one. Now if you do this one with the same, instead of 2, earlier you put 2 here, you put -2 here, you can put -1, it won't be in this region, it will be outside this region. -2, you must try out 1, -1, -2, you will see they won't be in this region, they'll be outside the region. So when you do -2 and calculate, it goes to 0. And when the edge that will be aliased to -2. So naturally you're going to see, you've got a signal going to be 0 and -2. So that region, this one is translated here. And if you continue and calculate that further, you will find this one is also, when you substitute -3, you will see it will be translated here between 2 and 4. So basically, all I am showing is from here the alias equation. When you have aliasing, you think there's no frequency here, because in the original spectrum, no frequency. Let me remove every writing. In the original spectrum, that's the region, half the sampling, there's no energy here. But you've got signal here. In this region, there's energy. And when you take the wrong sampling, you can see suddenly, this will translate in here, that will translate in here, and your output looks like as though there was signal in that region. You see? So aliasing, you have to be careful, very careful. If you cause aliasing, all sorts of things can happen. If you don't cause aliasing, you're not in trouble. But in some application, we really want aliasing to happen, because this is a bandpass signal. And we can move this band being occupying here, move it to low pass region. That's very good for detection of signal. So in some application, we want aliasing to happen such that a band pass signal is translated into low pass. Okay? Anyway, just go back to this diagram, and by following this equation, and you will find this true spectrum has been translated there, and here, and here. The shaded one will be this one, and the unshaded one is this one. So I would like you to really relook at this one very carefully and try this example with the different values, k equal to 1, k equal to -1, and you will see they will occupy in different positions here, outside this region. So it's important for you to try out. So in one hand, we say aliasing is not good to have it. That is definite. But in the other hand, if you are very careful, you can translate a bandpass signal into a low-pass region by causing aliasing. You need to think very cleverly when you are designing a system, but you will learn that slightly later, a multi-rate system in signal processing 2 in the 4th year, if you are still interested in this area to pursue further. Now we come back to our Chapter 3B. and which is Introduction to Digital Filters. Earlier we all studied as digital systems. Now we are going to put them all into filters perspective. So there are two types of digital filters available. One is called recursive. That means there is one feedback path at least. And then second called non-recursive. There's no feedback path at all. Everything is feed forward. So a linear, time-invariant discrete system described by the following equation is commonly called a digital filter. A digital filter output Yn has got a relationship with the input, that part is feed forward, and then, the whole lot, and then you've got a feedback path which depends on the output, previous outputs. So that's a general equation of a low-pass filter, of a digital filter, right? By appropriately choosing these coefficients, you can select low-pass, band-pass, band-stop, and high-pass filters. So, when Xn is the input signal, Yn is the output signal, A0, A1, V1, V2 are called constants, or they're called filter coefficients. These coefficients, which we will learn in chapter 4 to 5, how to actually calculate these coefficients, characterizes the system. It characterizes the system what it is. So I've written the equation again here for you. When Vk is 0, if you set this part 0, then you only have a feed-forward system. In this case, the filter is called recursive, non-recursive type. If Vk is not 0, that's when Vk is not 0, this is not 0, then you get the whole lot, and that's called recursive type because the output is coming in. When you have output, there's a feedback there. When you don't have, only output is feedback, is only feed forward, and then only it's based on current input in the past inputs. So it can be on past input only as well. So let's look at a non-recursive digital filter, which is sometimes called FIR, finite impulse response filter. We have looked at it before. So let's say Vk is 0. Then the calculation does not require the use of previous calculated samples of the output. We don't have any output in the equation now. We expanded, and the previous equation, this is the equation, this Vk is 0 now. So you got, these are the inputs now. So this looks like a convolution, remember? We have looked at it before. These look like the coefficients. But they are the coefficients. So this equation can be written as a convolution sum because Hk are the coefficients and Xn minus A is the other part. And at the moment, it looks as a convolution. So you can always see a FIR filter, a finite impulse response filter, the coefficient. Do you remember if you have a finite impulse response filter, whenever, for this filter, if you give an impulse as the input, the output is going to be first that coefficient, next that coefficient, and so on, last that coefficient, after that all the zeros will come out on the impulse response. We have looked at that before. So, therefore the impulse response is identical to the coefficient. That's the impulse response, identical to the coefficient. The coefficient will come out, m coefficient, and then 0. So take an example. Here is an example for the same equation expanded. The H naught is that, then that, and so on, Hm, and then all zeros. So any filter that has an impulse response finite duration, because all these will come out for finite duration. First output, second, third, fourth, fifth, nth, then it's all zero. So it's a finite duration. Then it's called finite impulse response filter. So basically we can say FIR filter has got only numerator, the equations are no denominator at all. And the coefficients are the impulse response. For those filters, if you give an impulse at the input, the output are the coefficients and then all zeros. Here is an example. Here is Yn. This is an FIR filter. There's no feedback path. And if you take the transfer function, take the transform and take the transfer function, you get A0, that's the A1 and A2. I've done this earlier. So it's only numerator equations. And because this second here is called second order FIR filter. A property of the FIR filter is that will be always stable, because zeros can be inside the unit circle or outside the unit circle. It can be anywhere you want, but it just be always stable, the filter. The stability requires that there should be poles, no poles outside the unit circle. This condition is automatically satisfied. There are no poles at all outside the origin. In fact, all poles are located at the origin in this case. So another property of non-recursive filter is that we make filters exactly linear phase. We can, with the FIR filter, you can have linear phase filter. So the ability to have exactly linear phase, and you might ask, what's linear phase? Okay, here we go. We take a signal and we find the magnitude response, like a low-pass filter, right? That's frequency. And linear phase means that frequency, that's the phase angle we calculate, it's kind of straight line. The phase is linear. So what's the advantage of having a linear phase? You might just ask, what does that mean in reality? Well, we explain them later on, but you will find that if you have an FIR filter here, FIR filter, with a linear phase, that means when you pass one frequency, when you have any filters, the frequency will arrive, because there's a delay always, arrive at a certain time. Then the next signal, next frequency, if you have another frequency, that will also arrive here, but at a different time. If it is not a linear phase filter, if it's a linear phase filter, the composite signal all will arrive at the same time at the output. That means frequency F1, F2, F3, F4, all whatever. So think in case of music signal. Music signal has sometimes no fundamental but harmonics, a lot of harmonics. And you want to make sure the music signal, when you filter them, they should arrive at the same time. If they don't arrive at the same time, there will be harmonic distortion. One comes first, one comes later, different frequency comes later, it causes problem. Therefore, for speech it doesn't matter, because the ear is not sensitive for phase delay. Whereas for music signal, it is definitely important. So if you are going to use filtering video signal or music signal, you will use FIR filter with a linear phase. That means everything arrives at the same time. When the signal passes through a filter, it modifies amplitude and phase. So always when a signal is passing through a filter, its amplitude is modified or unchanged, depends on the type of filter, and the phase is also modified. So there are two things that we define. One is called the phase delay, other one is called the group delay. You get two things, phase delay and group delay. So what is the phase delay? What's the group delay? If we consider a signal that consists of several frequency components, example speech, waveform, the phase delay of the filter is the amount of time delay each frequency component of the signal suffers in going through the filter. So you've got a filter, a signal has to go through, it takes a certain amount of time. That's called the phase delay. That is defined as phi theta, that's the phase angle divided by theta, a minus of that. It's called negative of the phase angle divided by the frequency. If you use positive, that's possible as well, but the delay is there, so we normally use negative sign. But you can, as long as you know you use positive sign, that's understandable if you want it, but the definition is delay. Then you have got a group delay. That's the second part. One is a phase delay, other one is group delay. Group delay of on the other hand is the average time delay of a composite signal suffers at each frequency as it passes through the input to output. Group delay means the whole group composite signal going through across rather than looking individual. How we do it, if we want to have the same group delay for all the components, we say the differential d phi theta or theta, the negative of the derivative of the phase. I think there's a mistake here. I think d theta, d phi theta, d theta is with respect to frequency. If this is constant, then you have got a constant group delay. That means every frequency will arrive at the same frequency, same time. So always for music signal, when you are designing a filter, you will say you want a constant group delay. That means every frequency arrives at the same time. That only can be done if this phase is a linear phase. If it's linear, you differentiate that this will be the slope. Slope is constant, so this will become as a constant. That means all the frequencies will arrive at the same time. There are experiments you can try out for these. So what is important is phase delay is understandable. It's not a major thing. Group delay is very important. Group delay means that group delay constant means the filter will make sure every frequency passing through will come at the output at the same time. They all arrive at the same time. So that's called constant group delay filters. That is linear phase filters. So if this is one example of phase, that is phase plot. How do you do phase plot? If you have got h theta, which is equal to a plus jb, your magnitude of h theta is square root of a squared plus b squared, right? And your phase of h theta r is equal to tan inverse b over a, and that depends on the frequency, because this all depends on frequency theta. So if you plot that for a linear phase filter, it looks like that. As theta varies, minus phi to plus phi, it's a straight line. Phi theta equal to minus theta. If you differentiate that, d phi theta over d theta minus d phi theta, it's a group delay which is equal to 1. So that means constant. A constant group delay means that signal components at different frequencies receive the same amount of delay in the filter. That means at the output they arrive at the same time. Okay? So signals like music signal has to be made sure that they must have, if you want to filter music signal, they must go through a constant group delay filter, that is linear phase filter. A filter is said to have a linear phase response as long as it satisfies this relationship or this relationship. They're linear phase. One is like that, going through origin. Other filter, F and phase, is like that. It's shifted, B minus A theta, just shifted by one value. So basically, we are defining FIR filter. We talked about FIR filter, but FIR filter, what we normally use is constant group delay filters or linear phase filters. They're exactly the same. So here are some examples of filters, and very basic examples. Two filter structures are shown below, and both filters have linear phase. You have to show. Okay, so we write the transfer function for that. We write the transfer function for that. And basically, by looking at, you will say, yz, what is yz equal? Over hz. You will simply say it will be 1 plus such to the minus 1 plus such to the minus 2. That's what you'll have here. Here you will say this all plus, yes. Here you will say hz equal to 1 minus such to the minus 2. That's all you have. Two different filters. There's nothing here in between. That's the minus 1 is not connected. That's not connected. So that's 0. So those two filters, if you take and go on to the next page, you've been shown that these filters, these are the filters. Here you go. That's 1. That's 0. Now I calculate h theta. Substitute. To calculate h theta, you substitute h stat and stat, you get stat equal to e to the j theta. Yeah? You substitute that, you get this. Now we looked at before, we try to take out this 2 theta there, e to the minus theta out of the bracket. So when you do e to the minus theta out of the bracket, that bracket should be there. That's not right. What will happen is, this will become, sorry. That's correct. Sorry, can I go back? This is correct. Now I'm taking e to the minus theta out. So this will become e to the plus theta. When you multiply this, you'll get 1. This will become e to the, I took e to the minus theta, so that will be the 1. This will have 1 e to the minus theta. Okay? Can you see that? I took e to the minus theta out. So this will give me e to the plus theta. This will give me 1, that's there. And this will give me minus gone, another 1 here. And if I combine these two, I know that is 2 cos theta. Remember we looked at it before? E to the j theta equal to cos theta plus j sin theta. E to the minus j theta equal to cos theta minus j sin theta. If you add them together, these two cancel out, you get 2 cos theta equal to this. So this is our equation now for h theta. When you have an equation h theta, then this is your magnitude, and here's the phase. The phase from here, remember if you take this one, it will be cos theta minus j sin theta. So you can find out tan theta, you can say phase is going to be minus theta, it's your phase from here. So from here we can read out the phase minus in theta, so we say that's the phase. That is linear, you can see that's a linear phase, because that's a straight line equation. Now go in here and write the same thing, that's that. Substitute, you can e to the 2 theta. Now try to take out e to the power of minus theta out. When you take e to the power of minus theta out, you get e to the power of j theta here for that. Because we multiply this, you get 1. And that will give you e to the minus j theta. Now, I know it's a minus sign there, so it's going to be sine. So I want to make sure we know if you have e to the j theta is equal to cos theta plus j sin theta, e to the minus j theta equal to cos theta minus j sin theta. If you subtract these goes, you get sin theta is equal to that plus that e to the sum over these two added up 2j you will get. So I need a 2j, so I put them there and I multiply the 2j there. So I can now group all these and say that part is my sin theta, which is there, and I got e to the minus j theta here. J can be written as e to the power of j pi over 2, because that's equal to what? Cos pi over 2 plus j sin pi over 2. Cos pi over 2 is 0, so j sin pi over 2 is j. J can be always written as e to the power of j pi over 2. So that's what I've written here, e to the j pi over 2. I now combine these two together, that will become the phase. And the magnitude is 2 sin theta. So phase is pi over 2 minus. This is also a straight line, but just shifted. So both are linear phase filters. Can you see that? Both of them are linear phase filters. Another thing that you will learn later on by looking at the coefficients. If you have 3 coefficients, if you get the center coefficient, and if these two are symmetrical around the center, then it will always give you linear phase. You will learn that later on. Take this coefficient, center here, these two are on both sides. In this case, they are not symmetrical, but they are anti-symmetrical. They also give you linear phase. Okay? We will come back to that linear phase filters later on. They're symmetrical and anti-symmetrical. Okay? So do you understand from a transfer function, how do you extract the phase information? Now we come to recursive digital filters. So that's all early digital filter. Now we look at recursive digital filters. Recursive means this part has to be there. Has to be there. Recursive filter. So, for example, I could give you a recursive filter as the first order filter of that difference equation, and if you take the transfer, the transform, you get A naught over 1 plus B set minus 1. This is called impulse, infinite impulse response filter. A recursive filter is normally a IIR filter. We call IIR because if you give an impulse here, this impulse response will never go to 0, but it will go down and it will approach to 0. So it's infinite. Response is infinite. So here are some examples of infinite impulse response filter. Here is a filter. This is a second order filter, but this is only an FIR filter, zeros only. There's only zeros, there is no denominator, except the denominator. If you do this one correctly, you will get A naught that squared plus A1 that plus A2 divided by that squared you will get. There is a pole here, there's zeros here, there's a pole here at the origin. Poles at the origin, poles at the zeros at the origin do not contribute to anything. They just there for normalization purposes. So this is only a FIR filter. This is an IIR filter, but this has got only poles. Certainly there are zeros at the origin, but leaving out that, it's an all pole. So this is called all pole filter. In this case, this has got zeros as well as poles. So this is an IIR filter because you've got a feedback. This is also IIR filter, you've got a feedback. This is only feed forward, that's FIR filter. These are some examples of IIR, FIR filters, and you need to know by looking at it what type of filters they are. Let's now look at another example where you've been given a first order IIR filter. It's the first order filter. The difference equation for that is this. You can try it out. Now I'm going to find out DC gain. What is DC gain? DC gain means in analog case f equals to 0. In the digital case we say theta equals to 0 and you get a DC gain. Right? And so in this filter you first calculate h theta, and when you calculate h theta, this will be e to the minus j theta, e to the power minus j theta, and when you put theta equal to 0, you get that equal to 1. So the DC gain becomes 1 over 1 minus a. In some applications where you don't want a DC gain, zero frequency should go without being attenuated or being amplified. In that sense, we normally take the transfer function and multiply the inverse of that, which is 1 minus, not inverse, reciprocal of that is 1 minus a. Now if you apply DC gain, this is 1, this will cancel out, DC gain will become 1. So the new transfer function with the DC gain equal to 1 is that now. So if you cross multiply and get the difference equation, you get 1 minus a xn ayn as opposed to xn times ayn. So no matter what transfer function is given, you should be able to calculate the DC gain and normalize the gain such that the DC gain is 1. In many applications, that's what you do. Some applications does not matter, but you should know how to normalize it. Let's take a low-pass filter here. And low-pass filter is given with this particular transfer function. And you've been told, determine B, the value B, such that H naught is equal to 1. H naught means is DC gain, H theta. H theta, when theta equals to 0, is called H naught, which is the DC gain. Then you have been asked to find out 3 dB bandwidth of the normalized filter. So you first normalize, then calculate 3 dB bandwidth. This is the first time you're trying to calculate bandwidth of a filter. So let's have a look at this question. So in this question, first, you write the transfer function and you get, this is your transfer function that you have, and you have been given h0 equal to 1, so substitute theta equals 0 here. When you do that, you get 1 minus a b over 1 minus a. which is equal to 1 is given here. So when you do that, b becomes 1 minus a. So the new transfer function is h theta equal to 1 minus a over 1 minus a e to the j theta. Now, if you want to find out the magnitude response, you convert them into real part, imaginary part, and then take the magnitude square root of real squared, that squared, plus that squared, so that squared, plus that squared. And if you simplify, sine squared, cos squared is 1, and you will end up, this is your magnitude response. So, to calculate 3dB, you first get the magnitude response. You got the magnitude response. Once you got it, you can then plot it. However, I would like to show you another method of calculating magnitude response. H theta squared first you calculate, which is defined as H theta multiplied by H star theta, which is a complex, which I have done earlier in an example in the part B, chapter 1 CD. So this is H theta, that's H theta, and when you say H complex conjugate of it, that minus theta will become plus theta, plus j theta. Okay. So if you multiply these two, you will get mod H theta squared, which is, if you multiply this out and expand it, you will get this, and then mod H theta is square root of that, and this is exactly same as what you got before. That's exactly same as what you got this. You can use this method, or you can use this method to get the modulus or modulus squared. So this particular filter is a low pass filter, and if you look at the DC gain is 1, that's 1, and if you want to find 3 dB, you go 1 over root 2, go down, and equal to, that's the cutoff frequency. Or you could say the power is 1 over root 2 squared. So we have got H theta squared, which is equal to a cutoff frequency, which is at that point H theta squared is going to be 1 over 2, because when you square this, you get 1 over 2. So 1 over 2 times of H naught squared, which is already 1, which is the half power point. Take the maximum value and go 1 over 2 for power. It is modulus 1 over root 2. If you do that, you say 1 over 2, which is the H theta squared, which is equal to this one. And that 1 over 2 happens when theta equals theta c. When theta equals theta c, that's where it happens. Now you cross multiply these and find out the value of theta c, which inverse cost inverse of this. And theta c is the cutoff frequency, can be calculated in terms of A. So you can see your 3 dB bandwidth is determined by your transfer function, the coefficient, which is Hz equal to 1 minus A divided by 1 minus A to the minus 1. That's your transfer function. This, by selecting this A appropriately, you can determine your cutoff frequency, 3 dB cutoff frequency. That's your bandwidth of your low pass filter. Consider another filter. This is another filter here, and we want to find out the magnitude response. I can say when these filters have got these coefficients, Z1 and that1, and that coefficient, when they both are equal, I can say this is an old pass filter. I know the properties, but you will learn that as you go along. Let's calculate its frequency response, magnitude response. So I go back again to the same principle, H theta squared I like to calculate. I first find H theta and its conjugate. H theta, by going back here, H theta you substitute, that equal to e to the j theta, you substitute that, and if you substitute that there, you'll get that. You make it as, don't take it, you rationalize this as c plus a to the minus 2 divided by a plus c to the minus 2. Make the transfer function like that before you substitute such equal to e to the j theta. Alright? So once you have done that, you substitute, that's your H theta. and that's become your H star theta, because this sign changes. And then when you multiply them out, that term cancel with that term is equal to 1. That means if you plot the magnitude response between minus pi to plus pi, the amplitude is 1. So it passes all the frequencies. Therefore, this is called an all-pass filter. It's called an all-pass filter. So given your transfer function, you can actually calculate the frequency response. From the frequency response, you can say what type of filter is. Or by looking at the transfer function, knowing the coefficient, you can also say what type of filter is. Now we look at the digital filter realization. The filters can be realized. We have already looked at this before, but we go a bit more detail. Digital filter realization is, this is our filter. If you take the set transform, y set equal to a x set minus k, the transform of that and that. And if you then combine them and make the transfer function, which is y set over x set, you bring this to one side and it becomes a k set to minus k and 1 plus b k set to minus k. And you know that you can write the transfer function in this form, write the zeros first and the poles afterwards, that's called structure 1. Or poles first and zeros afterwards, that's called structure 2. We have looked at it in a smaller order earlier. And if you draw the structures, let's go back. I'm going to draw zeros first and then poles. So if I draw, you already know how to draw the structure. It will be A0, A1 set to minus 1, A2, and so M those. And B is feedback path, this one, this one, this one. I just put them all in one summer just to make it simpler. And that's our structure 1, which is called the direct form 1. And if you switch them around, according to the second equation, so that's this one, poles first and 0 afterwards. So the poles come first, you don't change this, that remains same, and the zeros afterwards. You've got that structure, and you should put dotted line here. That's the structure, and that's called direct form 2. And if you combine these together, that's because they tap at the same point, the delays can be combined. And if you do that, that's called canonic form, minimum delay. A discrete time filter is said to be canonic if it contains the minimum number of delay elements necessary to realize the associated frequency response or associated structure. Now we come up with another realization, which is parallel realization. We haven't done this yet. Here is my transfer function. It could be any type of transfer function. It has got zeros and poles. It's an IIR filter, IIR filter. And I can divide this one by factorizing them or doing partial fraction. I can make this transfer function into small transfer function added together. If I do that, I get a parallel structure. So I need to find a way of doing plus. So this major transfer function can be made as sum of small transfer functions. That means same input via x. So for the same input, I've got a small function here, another one here, another one here, and I add the output. All of them are added together because plus 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 plus, you get output. That structure is called parallel. Like in the circuit theory, you would have done a parallel resistor like that, and 3 resistors in parallel, like this one. This is called parallel structure. So you must find a way of making parallel. We'll do in a minute an example. The second realization is called the cascade realization. Cascade realization means you factorize this, factorize the bottom, and make them as a small transfer function multiplied, not plus, now multiplied. So if you factorize them, they can be made as small of them. Now, for the same input and output, that's your first one, second one, third one. You put them one after another, for same output can be obtained. So it depends on your realization. You can go for cascade realization or parallel realization. And let's take some examples and demonstrate these realizations. So here is a parallel realization of a third order system. Here is a big system given to you. And I need to know how to do partial fractions. You've already done this. Look at it here, order 1, order 2, so it's the third order here. And also look on the top, it's also third order. If you've got equal orders on the numerator and denominator, you will have a constant first. And then you've got a constant divided by the first whole. And if this is a second order, you will have a first order there. You can have a plus or minus, it doesn't matter. So I can divide this major structure into 1, 2, 3. Let's go and look at these values. I can show by doing the partial fraction, the values are going to be 19 over 3, 5, and 23, 1/3 23. That is my structure. And in a normal structure, you don't leave 5 in the front. You take out 5 out, common out, and it should be 1 plus. That's how we know how to do implementation. So you divide everything by 15, so each coefficient. These are the coefficients. So my parallel structure is that constant plus that implementation and that implementation. All 3 output together will give me a parallel implementation. So let me go back to parallel implementation. What my parallel implementation is? First one tells me 19 plus 19 over 3 from the input. This is yz over xz. Yeah. So let me go back. I got from x, I got that. Fine. Then go back again. I need this one. 5 over 2 times that. That's the first order recursive filter with a coefficient of 0.5, which is minus 0.5. So let me go a recursive filter with the coefficients of minus 0.5 for the same input, and it has got minus 2.5 in front. Isn't that right? Because there's the minus 2.5 here. That's the constant there in the front. So that's here. Then you've got the next order is this one. It's a 0 there, and it's a whole second order. So it's 2 delays on the forward and 2 delays, well, 1 delay in forward and 2 delays in the backward implementation. If you implement that, you will get canonic structure. There's 1, 2 delay there, plus 1 delay here, and that one. Added them up, there's 1 output, second output, third output. If you add all these outputs together, you get Yn. So this is a parallel structure. Now, same transfer function, I want to now convert them into cascaded realization, same transfer function. So what I'm going to do is I'm going to make sure I'm going to factorize these. I could take 1 plus z minus 1 common, or divide by that, and 2 plus z minus 1. So this becomes 2 second order. So I could say I have a transfer function of first order followed by a second order. It's a major example, but in an example you get a simple one. So now if you take out these coefficients and make them as, well, that you don't need to do anything. Here, you only have to divide this by 23 and the coefficients are set up. This is an easy structure now to implement. So remember, this is factorization you have to do to make it cascade. So if you do that, you got a structure here. That's your first order structure giving this equation, multiplied by a second order structure. A second order structure here, you multiply the first order structure and same input, and you get the same output. So I have shown you a parallel structure where I had output there and output another filter, and 3 of them added together against a cascaded structure. So it depends on the transfer function, depends on the question, you have to do it. You have to decide whether you have to factorize or whether you have to do partial fraction. That's all you have to do. Here are some examples. here's an implementation. All coefficients are real. So you can do this in cascade. So in order to do in cascade, what you do, you make them as 1 over 1 minus a, that's the minus 1, multiplied by 1 over 1 minus b, that's the minus 1. You've got that. So you implement the first one, that is that, multiplied by the second one, that is that. You get the answer. So that's the simple cascade structure that I have done. Take another example. Here is one single structure. Direct form. They ask you to implement this in direct form as well. Where is it? Direct form 2. That means the direct form means you multiply this out. Just multiply them out. When you multiply them out, that's what you get, and implement that equation. That gives you the direct form. Okay? And then you are asked to implement, sorry, let me go back to the equation. Cascade form, I've done. Direct form, I've done. Parallel structure. So that means I have to go back and take this equation and make it parallel. How do I make it parallel, that equation? You put them as partial fractions, plus, plus. So the equation I had was what? H dash is equal to 1 over 1 minus a, that's the minus 1, multiplied by 1 over 1 minus b, that's the minus 1. That's what I had. I now make them as plus by having two constants. So if I do that, then you will find I have a structure, and I know how to calculate a and b using partial fractions, and I get these values. I leave you to work it out. Once I have that, these are multipliers. So here's the multiplier. So you do that first, which is that comes in as our first one, and multiply by that, plus you get this part 1 over b minus that, that's that one, and multiply by b over a plus b, you get yn. So that's your parallel structure. So I've shown you a very simple example where you have got cascade structure and parallel structure. Similarly, another one here. Here, this one is 3 of them. This can be written as 1 over 1 minus a, that's minus 1, times 1 over 1 minus a, that's the minus 1, times 1 over 1 minus a, that's the minus 1. So 3 of them. So I do the first one, and then the second one, and the third one. And all 3 give me in parallel a cascade structure there. And if you want direct form, you just multiply them out. When you multiply them out, this is your new transfer function, and you just implement the direct form. There's 10 to the minus 3, that means 1, 2, 3 delays, and the coefficients appropriately you draw. Go back. So there's no parallel structure exists because partial fraction expansion cannot be performed. So there's no parallel structure for this. Now let's come on to look at this particular structure. You have been asked to draw. There's one parallel structure. Another example, and you can make them as cascade. From here, just cross multiplying these, you get cascade structure. So if you take the parallel structure, I just separate them as 1, 2. Separate this as 1, 2. So I got 2 things in cascade. That one and that one in cascade. These 2 are in cascade. That one and that one in cascade. That's these 2. And then both output, that output are added together. So that output comes here, this comes here, added together. That's the parallel structure for this equation. What is the cascade structure for this equation? You cross multiply these and do the factorization there, or multiply them. When you do that, you get a transfer function of this one. you can prove that one as one structure and then 1 over that one as the second one. So they both will be in cascade. So if you do that, you can see one is the one I selected and the second one is here. I get a cascade structure. So you can have both. You should try this out yourself and see whether you can get this cascade structure. The next section, so far we looked at the structure, how to implement direct form 1, direct form 2, canonic form, then parallel and cascade. And we looked at various examples. Now we go back and re-look at again the magnitude and phase response, how to calculate, how to plot the magnitude and phase response. So that's the next section, magnitude and phase response. We can actually prove and we can show, which I'm not showing you, but it's explained on the reference book, textbook. You can show that magnitude response is an even function and the phase response is an odd function of frequency. We can show this, but we won't spend time proving that. You can assume and you can look at the reference books that shows how to prove it. Okay? Now we use this principle and we will just go through various examples in a minute. Here's one example where we have to calculate the magnitude and phase response of a 3-sample averager. 3-sample averager means, in this case, the coefficient 1/3. That means if you work out this, the transfer function, it becomes as 1/3 set to the minus 1. 1/3 set to 0, 1/3 set to the 1. And that's what is given here. N is between -1 and +1. And that means you can see that signal and that output and that all three output are added together and divided by 3. That's called an averager. As soon as you add samples, an averager is a low-pass filter. We know that. Adding samples is averager, which is a low-pass filter. If you subtract 2 samples, then become as a differentiator, which is a high-pass filter. So if this is an FIR filter, no poles at all, it's all zeros. There are poles at the origin, but we are not worried about that. So let's take this example and we'll work out our magnitude and phase response. If you go and substitute that equal to e to the j theta, you get that equation. From that, by combining those two, you can say that's the cosine, so it will work out to be 1/3 2 cos theta. That's our h theta. But when you are drawing this, you can draw magnitude response without any problem, but you must take precautions. The precautions are that when you draw phase response filter having real value, you will find that at some places, you can't just simply say that this magnitude response, in this case is okay. In some cases, when theta is pi, this will be a negative value. If this was 1 and this was 1, h theta will go 0. So that means there's a change on phase response. Wherever magnitude goes to 0, there will be a change. But not in this case, but you just have to be careful on that end of it. Well, first time I'm introducing it, so it's a bit difficult to grasp it. Let's look at the next slide. So what I'm trying to say to you is that you can consider the following linear phase function where linear phase means that v theta e to the j k theta and phi theta from here is minus k theta. So if these are real value functions, you can say h theta equal to v theta cos that, this will be v theta j sine, which will become as lava. Well, cos k theta is cos theta. So if we calculate the angle is tan phi, which this divided by this is equal to minus tan k theta. So that means phi, the phase angle, automatically, I'm proving phase angle, automatically is minus k theta. So you're trying to do phase theta, like you write k theta normally, yeah? Minus k theta. That's all I'm trying to show here. So you find phase angle is minus k theta. This phase function phi theta includes linear phase, in this case linear phase, and also accumulates the sign changes in b theta. So go back and see here, when you are using this phase, if the b changes, if b theta changes sign, that can change the phase as well. For example, say b theta equal to -1. So I could write that e to the power minus e to the power of j pi, which is -1. So you can see immediately there's a change in the phase. So we can't just simply say b theta is the magnitude. Okay, that's what we said earlier. But that has got a contribution to the phase, depends on this value. So that's what we are trying to say here. Since -1 can be expressed as a jump of plus or minus j pi, we look at frequencies where b theta changes sign. So if b theta is positive, then phi theta is that, no problem. If b theta is always positive, there's no difficulty at all. So we are saying h theta is equal to e to the power minus j k theta times b theta. If b theta is positive, no change, that's your phase. If b theta is negative, this will give you a plus or minus pi. That has to be added to the original phase. Remember that. Okay? Let's go back to our example. This is our thing, and if we take the magnitude of that, that will be the magnitude. There's no problem. And if you look at the phase, like basically by looking at there's no phase part here, 0. But phase is 0. When that's true, when your h theta is positive. If this is positive, no problem. If this becomes negative, which will happen when theta equal to plus or minus pi, then this become negative, means the -1 comes into play. That means I have to put the e to the power j plus or minus pi has to come in. Immediately your phase is, original phase 0, plus or minus pi has to come in. And you will find in this region, and this is not omega, this is theta. In this region, this is always positive, no problem. But in this region, these two regions, this will be negative. That means additional phase comes in. So let's plot this, what happens. Here is your graph. Here is the h theta, which I am plotting. What is h theta is? Go back. H theta, what h theta is that? 1/3 1 plus 2 cos theta. This is 1/3 1 plus 2 cos theta. And this is positive in this region, fine, no problem at all. Because I'm taking modulus, everything looks positive here. Right. But you will find that region, we take that region, we are not worried about, we always worried about minus pi to plus pi. We are not interested in this because it will repeat. This will repeat, we know. Only. And you will find, if you don't take the modulus, this will go down, negative, this part, this will be negative. Negative means I've got a phase change. So during this region, you find my phase is 0. During this region and this region, my value h theta is going to be negative. That means I have to have a phase jump of e to the j pi, which is plus or minus. So if I am jumping at that point minus pi because I'm going to go negative in h theta. Then it's an odd function, therefore you should make sure this side you go positive. Okay? So the clue always everybody look at is this. In the magnitude response, when there's a 0 crossing, touches the 0, then at that point there will be a phase change. See? And the phase will jump by pi. Because h theta is positive, no problem. H theta becomes negative. That means, say, minus pi, you write as minus 1 multiplied by pi, which is e to the power plus or minus j pi times pi. This is corresponds to minus 1. that means the phase. So that's this the phase comes to play. So when you are drawing phase plot, you just have to be careful there. Let's take another example here. In this case, you've been given H0, H1, H2 is given, and you write the transfer function based on what you are given. That's your transfer function. And the transfer function from that H theta becomes that. I don't need to run through this because you substitute that equal to e to the j theta. Now always you take out what e to the minus j theta out. When you take that out, this will become half e to the j theta. This will become 1. This will become half e to the minus j theta. You can combine that one and that one and make it as a cos theta. So that's cos theta and that. Now what happened? What is your phase? It's minus theta. Very good. As long as b theta is positive. If b theta is negative, then minus pi or plus pi will come and add on to that. Remember that. So let's plot this. H theta. I plotted them from here to here is even function. What is H theta is according to our equation? 1 plus cos theta. So H theta is 1 plus cos theta. That means theta equal to 0. You put theta equal to 0, this will be 2. Theta equal to pi, 1 minus pi is 0. So it's a low pass filter. What happened to the phase according to this? Phase is minus theta, okay? But d theta, during the region I want, pi is always positive. Therefore, there is no phase jump. It goes from a straight line. There is no phase jump at all for me. It just goes from there, and then at here it will go in parallel outside. They're just duplication. So it's an odd function. It's an even function. Even function means it's symmetrical. If you do it, it's symmetrical. Odd function is not symmetrical. Either that quadrant, or that and that is odd function. Take another example. Delta n is equal to 1. N equal to 0, otherwise 0. Let's take the transform of that. It's 1. H theta is also 1. What's the phase? You take H theta, phase is 0. So it's a 0 phase, low pass filter passing every frequencies without any problem. That's the impulse response. So if you say this is the H stat, also 1, H theta, also 1. Alright. Let's take another example where Hn is delta n minus k. Signal is shifted. So this is your impulse now at k position. And people will say, it's only impulse shifted. Yes, no change on the maximum response at all. But what will happen in the phase? There will be change. Let's look at H stat is equal to set to the minus k. We take the set transform of that. H theta is e to the minus k. So magnitude is 1 and the phase phi theta is equal to minus theta k, minus k theta. So if you plot that, what will happen? Okay? So magnitude is 1. K, we don't know what value k is. K is 1 or 2. So you just will go up. When it reaches pi, it will never go over pi. The phases are. Then it's wrap around. It gives a jump of 2 pi here. That's pi and a pi, 2 pi. And then just goes parallel to that. So when you draw phase plot, you never allow the phase to exceed more than pi. You wrap around, you bring them down, get a 2 pi jump, and then redraw them. Because we don't know what value of k is going to be and where it's going to happen. So this is the way phase plot is drawn. Phase plot is drawn with maximum pi to plus pi. If it reaches pi, then it will swing by 2 pi down and then go again parallel to this. So that's how you draw phase plot. Look at the phase plot. When phase exceeds plus or minus pi range, a jump of plus or minus 2 pi is needed to bring the phase back to plus or minus pi. Otherwise, if you draw the phase plot, it will keep going up to infinity and we have no idea what it's doing. So we don't do that in phase plot. In MATLAB also the same. So phase jumps are very important. From the previous example, we note that there are 2 occasions for which phase experiences discontinuity or jump. A jump of 2 pi occurs to maintain the magnitude and phase function within the principal value of minus pi to plus pi. A jump of plus pi occurs when b theta undergoes a change of sign. If the change of sign in the magnitude of b theta, then it's jump of pi. Otherwise, 2 pi jump. And I can only explain this further using few examples. So let's go back to these examples and we start here. Here is our previous adder. Here is given now 0, 1, 2. So 3 values. So that's here. It's again a low pass filter. Adding means low pass filter. That's my h theta. And then I take theta e to the j theta out minus j theta. That becomes cos 2 theta. You have that. You know by looking at here, the phase theta equal to minus theta. You have that. So you have that here. And that is only true when this b theta is positive. And we know this is true, b theta is only positive in that region. If theta goes anything outside the region, b theta becomes negative. As soon as you become negative, you must add a plus or minus pi to the original phase, which you do in 2 places. So let's start here, plot the magnitude response, the magnitude of that. When I plot it, I get up to pi over 2, that's positive, and you will find here it will become negative, but because of the magnitude. But wherever zero crossing there's a zero crossing, there's a crossing. When that happens, your phase, which is minus theta, goes from there to there, or there, it was going to go further, because it was planning to go further, it can go further, because at that point it crosses 0, so it must jump by pi, jumps of pi, and then just continues. Similarly, it just goes up to here, and jump by pi, and then continues. That's the pi jump when it sees the change in magnitude crosses a 0. Take another example here. Determine a sketch of the magnitude response of phase of the following filter. There's a filter 1, 2, and 3. And 3 of them we're going to do, and you're going to see the difference. So let's go to that example. Take the first example. It's a differentiator. We're subtracting 2 samples. It's a differentiator. This is just a scale factor. Right? I write down the transfer function, and that becomes that. Then I find out the phase, the magnitude frequency response. You substitute that equal to the j theta, that's what you get. Immediately here, you can't take e to the minus j theta out now. You take e to the minus j theta over 2, half of that. When you do that, you get that form. And you know something is missing. To make this sign, you need to have a 2j in the bottom. So you put a 2j and multiply by 2j somewhere, and that becomes sine. So that becomes sine theta over 2. That's sine theta over 2. This is already this. A j, this 2 will cancel with that 2. A j will give you what? J equals to e to the power of pi over 2. Remember, j pi over 2. Which is cos pi over 2 plus j sine pi over 2. That is 0. So sine pi over 2 is equal to 1. So it's j. J is equal to e to the j pi over 2. So you put in here e to the j pi over 2. Add them together. You get this is your phase. This is your magnitude. So if you plot this sine theta over 2 on the magnitude response, it will be like that, and it's reflected there, exactly symmetrical. But don't forget, there's a zero crossing. At that zero crossing, you must have a phase jump of pi. So there's pi over 2 here, pi over 2 here. Total is pi. And from that point onwards, if you plot that, it will go cos theta over 2, that's in parallel to that. That is that equation. You put theta equals 0 here, so how do you plot this? Very easy. This is equal to pi over 2 minus theta over 2. Just put in theta equals 0 here, it becomes pi over 2. And from that, you draw that. Once you draw that, that part is orthosymmetric. Here's the second example. In this second example, you got 10 to the minus 8 because pi minus 8. So you draw that, you got 8. So now what you do, you take half of that out, so e to the minus j theta, so that comes in. You multiply by 2j and 2j, make this as a sine, so it's a sine 4 theta, and this one. And 1j will become as e to the j pi over 2, and then the 2 will be here. So the equation now becomes, these two added together, it's the phase there, and 2 sine 4 theta. Now 4 theta means it's going to cross 4 times within a pi. 4 zeros you're going to get it. So there's a 0 here, pi over 4, there's another 0, another 0, another 0. So what will happen to the phase? Look at that. Theta equals 0, it starts at pi over 2, start from pi over 2. It has to jump pi, right? So, like, not at that point here, it's pi. You don't need to worry about this. Let's do this one first. So, from here, it's going to follow minus 4 theta. It follows that. And it has to jump at that point, pi jump. Then it's going to follow 4 theta. And it has to jump pi. Then it's follow 4 theta. It has to jump pi. And follow, and so on. And you continue this one for negative as well. So that if you fold it, it becomes an odd function, not as even function. So it has to be careful what you're trying to do here. The last example is a basic signal delayed by 4 samples. So you are saying I'm only shifting the signal by delay, so no magnitude change. But there's a phase change. When you shift the sample by 1, you're causing phase delay. Have a look here. This one. And why is that? Is that one? You have to do that. H that is that. So H theta is e to the j theta. Mod of that is 1. So the magnitude of response is 1. Shifting a signal 10 to the minus 4 is that, but it causes phase delay. What happens to the phase? 4 theta, right? Theta equals 0, it's 1. So, where is it? 5 theta equal to minus 4 theta. So, theta equals 0 is 0, so it starts from 0. And it will follow 4 theta, it will keep going. When it keeps going, it reaches pi, any maximum value. Because magnitude doesn't go to 0 here. It goes pi, it can't go any further, pi. Then it will give a big jump of 2 pi jump. Remember, 2 things will happen. When the magnitude goes to 0, it's switched by pi. When there's no magnitude going to 0, but just phase is going, phase has switched plus pi, it will switch by 2 pi, and then go to 4 theta, and then reach pi, and 2 pi, and jump, and then so on. And that's how the phase response is done for that. The last couple of samples, all this time we looked at FIR filter, linear phase, they were linear. Now we look at an IIR filter. It's a low pass filter. You see that? Depends on the value of A. That's your transfer function from here. That's your H theta. And then we know how to get the magnitude. We know how to get the phase. I don't need to go through this detail. You know how to do it. This is H theta. This is H star theta. Multiply the amount, and you get from that real part, imaginary part, if you want. And well, it's a couple of ways of doing it. One is you can do this way to get the magnitude response. If you want just phase, you take the real part and imaginary part, right? And if you take the real part and imaginary part, you will get tan phi is imaginary divided by real part, and phase is that. Naturally, you can see this is not a linear function. So if you plot the phase for an IIR filter, and its magnitude response, what we have calculated before for this, is using this technique, you will find it's a low pass filter, and at that point, it will be, magnitude response will be 1 minus A, that's a DC, 1 over 1 minus A, then it comes to 0 here at A equals 0.5, and it doesn't go to 0, it stays there. If you plot, that's the magnitude response. If you just substitute and plot that as an even symmetry, so this side has to be the same as that side. And if you plot the phase response based on the previous equation, you can use MATLAB to do it, and you get the phase like that. It's a non-linear phase. It's not linear. So you will see for any IIR filter, the phase response is going to be nonlinear. There are just a quick example here. It's a low pass filter, H1 sub given to you, and we were asked to calculate K0 to make the DC gain 1, which we know. We just make this equal to 1 and then reciprocate, and that would be your DC gain, right? Whenever you want theta equals 0, you want to put theta equals 0 in the equation, that's equal to minus 1 equal to 1. You can substitute like that. That's not easy to do. So if you put that, that's the gain. So K0 will be 1 over 1 minus A, so that the unity gain is theta equals 0. And in this example, you want to find out what's the DC gain K0. You will find, before you find K0, to make a DC gain, if you find the DC gain, you get K0 is equal to this is 1, this is 1. So it will be 2 over 1 minus A. So if you want to make the DC gain equal to 1, you have to select K is equal to 1 minus A over 2. And if you do that, they do cancel out and give you the DC gain of 1. If you draw both filters, you can see this is a low pass filter, earlier one low pass filter, and this is also another low pass filter. They're both low pass filters. And if you plot both of them, and you will find one of them is inside, that's the H2 theta one, compared to the H1 theta, which only have pole, which only have 0, this only has 0, so that's the outside one. The one with the pole comes there, it's a better low pass filter. So you prefer to use a low pass filter with the pole there, rather than 0 only, in a lot of cases that you prefer. Now if you want linear phase, then you will go for the FIR filter. So you can just plot this one in MATLAB as well. You can have a look at it. If you want a high pass filter, how do you obtain a high pass filter? Simply, if you want a high pass filter, you put a minus sign here and put a plus sign here. So if you look at the H2 that you had, which is we had K0 over 1 plus e to the minus 1 over 1 minus A e to the minus 1. That's what you had. That's the low pass filter. If you change the sign for a high pass filter, this is different. So this becomes minus. If you make this is minus and this is plus, that's what I have done here. That filter will become now as a high pass filter. You can see that. Its modulus is high pass filter. So we can simply take one or two examples of a low pass filter, high pass filter. Here is a low pass filter. Adding 2 samples, that is adding 2 samples, it's a low pass filter. Subtracting 2 samples, that's a high pass filter. So you can just prove, you can just use H theta and calculate H theta, and in this case, if you do this one, you can show it's a high pass filter. And if you square it further, that means 2, if you have squared, that means 2 high pass filter in cascade. So the response will be good, sharper. So if you go there, and you can see it bends here and gets sharper there. And if you cube it, it gets further, because you've got 8 1 minus cos cubed, 4 1 minus cos squared. First one was 2 1 minus cos theta. So that's the graph for first order, second order, third order. Same filter, 3 times you have put in. 1 is 3 there. That one again 3 times you put in, and that would be the plot. And the DC gain is 8, 4, and 2.